I'm Vidit. I'm a PhD student at EPFL at CV Lab. And I'll be talking about this work which we did in collaboration with SBB about how to use synthetic data for mobile object detection. Before going forward, I would like to show you a video which explains a bit more in detail about the project. So this is a prototype that we had. Is showing that we want to overlay in the real train station these kind of components which we obtain from BIM models, which are building information models, which are textureless, but they show what objects should be in place at the train station. Over here, there's the clock, LCD screen, and escalators, which are present in the scene. And to get to this point, or to have such thing which works in the real scenario, one of the components that is interesting and we want to put into the development of this prototype was the object detection. Now I would zoom out to what object detection is to just give you a picture. To train an object detector, we need a so-called label data set where you have annotation for bounding objects, where objects are, and the class for that particular bounding box. And in typical scenario, when you have thousands of examples, you can attain a score, which on the very right represents how good is your object detector. And normally, for the real data sets, it hovers around 50, 60 MAP score. Problem with the label data set is like it's hard to attain, and it's costly to annotate the data. And the other direction where people put their effort in is trying to do some kind of few label data annotation and then train or fine-tune the network on those on those annotation. And what you can see is like you won't achieve that good performance if you just annotate with few examples. So what happens when you have no real, so we switch from a real scenario to synthetic, where we can have such information from the synthetic world. And in this particular case, we have information from BIM model. And we have the model, and then we overlay the texture on top of whatever is in the train station. So it is this bare bone of the train station. We overlay different textures and try to simulate different lighting condition over here. So it's all synthetically done. And what we can get essentially after you have developed this model is a bunch of annotation that we can get, and to an extent it's a diverse scenario that is represented with different day and night scene, different background, different angle, distances. But the problem is that once you train on synthetic, just on synthetic, it might not reflect what the real world pictures look like. And there's a shift between real world and the synthetic world. So I'll talk about two methods which we use to close this gap. Firstly is domain adaptation. And how we define domain adaptation task is that we have two domains, source and target. Source, we assume that we have labels available for the source domain, and target domain, we don't have any labels. So in this case, synthetic image is the source, and the target is the real world image. And to give an example on type of the assumption that we make is that input side distribution is different. In this case, when you imagine like MNIST, which is a black and white image versus colored image, if you pass it through the general feature extractor of a deep learning model, you have a distribution shift. So if something is trained on left-hand side kind of image, you won't achieve that much or that good performance on the right-hand side image. So the job of domain adaptation is to align the features which you have for the input shift. And one of the method which we used was this adversarial learning. So not going into much detail, you have three different colored components, green, purple, and the pink. So what we have as an information is that I have input image, which is a source domain image or target domain image, and I have only annotation available for the source image. So what happens is like if, so I have my domain label, which is available for all the input X. And the job of this training setup is that to confuse this module, meaning if it gets confused, it would try to align, it would happen only when the features of the source and target are different. And by training in this adversarial fashion, we can align or hope to align the features. So we take normal SSD object detector, apply these adversarial discriminators, and try to align the features of different images. And over here, putting some numbers. Okay, so we tried on like training with just 1,500 synthetic images for 5 classes that we had, which are different available objects on the in the train station. And we tested on real images. And just with this, compared to synthetic image, versus when we apply domain adaptation involving unlabeled images, we have improvement in different categories. There are a bit drops also, and, but relatively it was on a smaller set of test images. We added a bit more images, which we could find for 3 of the objects. And over here, we still have gain, but then there are different categories which perform poorly with the adaptation technique. And this brings into looking into issues that we might not be able to handle directly in the adaptation method, or is these kind of scenarios where we assume that there is a shift in the input domain, but now instead of having more shift in terms of representation, so the assumption is the object is represented similarly in synthetic and the real world, but over here there's a big geometrical shift or some kind of category shift as well. So this was supposed to be recycle station. This is also recycling station. So it represents a quite different representation of the same category. So these kind of issues are still lacking in our training setup. So we definitely fail on such scenarios. Going to how to tackle that, we switched to relatively simpler method, which is pseudo-labeling. So what you can have is you train your detector on synthetic images, you generate the predictions for whatever was trained on real set of images, and then you can retrain the network or kind of fine-tune on these generated labels. So what would happen is like you are bringing whatever was trained with the synthetic image closer to the real image space. And we threshold whatever prediction we use to retrain here is above 50% confidence. And over here, what I would like to show is like, okay, there is a boost from just using domain adaptation, but there's a much bigger jump from synthetic to the pseudo-label space. So this simpler technique is still very robust in this scenario. And so all the previous examples were for SSD. We trained with YOLO and added all the default augmentation and trained with, again, pseudo-labels. And over here, the performance, the jump is significant compared to the previous one. And we are closer in this case to some of the categories what the just training on the real images can do. And to talk about some of the improvements, like some of the shifts which were missing can be recaptured in, which were missing in the domain adaptation, which are captured back in the pseudo-label technique. To summarize what are the challenges or what are the ingredients needed to make it work, or why it's useful to use domain adaptation, because you don't need a so-called real label on the data set. But you do need synthetic images, which to an extent reflect to the objects that you're interested in or scene that you're interested in. And definitely, as in case of real images, you would need a diversity and force in the synthetic labels. With the pseudo-labels, so you have to, if you're training with or generating pseudo-labels with synthetic images, then definitely you need to be closer to what your use case is, where you can quickly leverage or kind of bootstrap to the unlabeled images, get not exact annotation, but kind of soft labels on the real images, and then try to retrain your network. And the challenge over here, the bigger part, is how to handle false positive and class imbalances when you're training. There are different techniques to do that when you try to handle class imbalances with reweighting different classes, and also to handle false positive is not to go on train a lot with the strong negatives. So with this, I will end my talk, and I'm ready for question. Thank you.
Yeah, thank you for the talk. I was just wondering, the initial BIM model that you used of the train station, how much work, do you know how much work it is to create such a detailed BIM model?
So in case of, so this project was with SPB, and what they have is, like, whenever there is construction going on in the train station, they have kind of a twin that they have to go, somebody has to go and do it. So there's already in pipeline, when something has to be added to the train station, they'd go and do it in the BIM model by, I don't know, like if there is somebody hired specifically to do this structure design, but they have this component in place that whenever there's things added or removed from the station, somebody is in the job to update the BIM model as well. And depending on the time, I'm not sure how much expertise it's needed, but there is a dedicated person who works with the BIM models. Yeah.
Okay, but do you know, because I think there is also the option, for example, to use GTA 5 to generate some data.
Yeah.
Would that differ a lot from the quality of the data of a BIM model? Because I think the graphic style is a bit different and so on, but I was just so curious.
So you mean, so BIM model is like bare bone, there's no texture at all on the models. So you, in this case, when we put the image, so somebody, either they have like some example texture, which they overlay on the scene. But to an extent, means I would not say that you can diversify by just putting random, like if you take from GTA scene, you would expect to put like a random texture in the train station. But it would, in your training process, that would increase another kind of shift is concept shift. That if you're trying to model a train station, you would not expect like, I don't know, means you don't expect a lot of clutter in terms of on platform. So it has to be closer to the concept of the train station, but you can add random textures if possible, if you want to. Yeah.
I see. Thank you.
Yeah.
So as additional information at SPB, we don't have all the BIM models for all the stations, but we will create them actually for the main stations because we can use the BIM models in many cases. Yeah, I don't know how much work it is, but it seems like a lot of work, but actually those companies are really fast doing them. So. Well, I don't know why we should create a virtual, imaginary stations.
I mean, it's just data annotation, right? If you have a few models, like your model comprises of an entire shaft or an entire station, you could configure it in several different ways, perhaps.
Yeah, but I think in this project, we assume that we kind of have the BIM model and we can use the existing models. So the idea was not to create a new station. So. Okay, thank you, Vidit. I think we go forward.